Imagine a colossal blue supergiant, a celestial titan dwarfing everything in its vicinity. These stellar behemoths are among the largest and most luminous stars in the cosmos, radiating energy at an astonishing rate. Hundreds of times more massive than our Sun, they represent the upper echelon of stellar existence. To put it into perspective, if our Sun were the size of a marble, these supergiants would be the size of a small car. Their sheer size dictates their tumultuous lives. Blazing for millions of years as a cosmic furnace, these stars are not just shining, they are actively forging the very fabric of reality. Within their cores, nuclear fusion is working tirelessly, converting lighter elements into heavier ones. It forges the elements of life, the carbon, oxygen, and nitrogen that make up our bodies and the world around us. These elements, born in the hearts of dying stars, are the building blocks of everything we know, its light a beacon across the universe, a testament to the immense power contained within. This light travels across vast distances, carrying with it the story of the star's life and the elements it has created. Yet even the brightest stars must die. Their immense energy output comes at a cost, a relatively short lifespan compared to smaller, more stable stars like our Sun. As its core runs out of fuel, the delicate balance between outward pressure from fusion and inward pressure from gravity begins to falter. The star's fate is sealed. Gravity overwhelms. The relentless force that has been held at bay for millions of years now asserts its dominance. The core begins to contract rapidly, and the star's outer layers swell and then collapse inward with incredible speed, triggering a chain reaction that will reshape the cosmos. This is the beginning of the end. In a final act, it explodes as a supernova, a cataclysmic event that releases more energy than our Sun will produce in its entire lifetime. Outshining entire galaxies for a brief moment, the supernova is a spectacle of cosmic proportions, a fleeting glimpse of raw power and destruction. The explosion scatters elements into space, enriching the interstellar medium with the very building blocks of future stars and planets. Seeding new stars, these elements become incorporated into swirling clouds of gas and dust, the nurseries where new stellar generations are born, and planets, providing the raw materials for the formation of new worlds, potentially harboring life. The cycle of stellar birth and death continues, but the core's fate is stranger still, its destiny determined by the star's initial mass. What remains after the supernova is a testament to the extreme forces at play. For the most massive stars, those behemoths that truly push the limits of stellar existence, an even more bizarre fate awaits. Gravity crushes the core beyond comprehension, overcoming all known forces and pushing matter to its absolute limit. Past the density of an atomic nucleus, where protons and neutrons are squeezed together into a single, unimaginable state. This is the birth of a black hole. An event horizon forms, a point of no return in the fabric of spacetime. A place where gravity is so intense it warps the very fabric of spacetime, creating a bottomless pit in the universe. Not even light can escape, forever trapped within the black hole's inescapable grasp. The ultimate cosmic prison. The laws of physics seem to break down here, pushed to their absolute limits in the face of such extreme conditions, creating a mystery at the edge of knowledge, a frontier where our understanding of the universe falters. The star's death gives rise to one of science's greatest enigmas, a puzzle that continues to challenge our understanding of gravity, space-time, and the fundamental laws of the universe. What truly lies at the heart of a black hole? What secrets are hidden within its singularity, a point of infinite density and mystery? A black hole. The very name evokes mystery and intrigue. It's a region in the vast expanse of space where gravity reigns supreme, an invisible force so intense that it warps the very fabric of space-time. Within this region lies a boundary, a point of no return from which nothing, not even light, can escape its relentless pull. This boundary is known as the event horizon. It's not a physical barrier but rather a theoretical surface, a point of no return. Once crossed, there's no going back. The event horizon marks the edge of the black hole's influence, the point beyond which escape velocity exceeds the speed of light, the ultimate speed limit of the universe. Imagine a cosmic waterfall, a cascade of space-time itself. If you were to cross the edge of this waterfall, the event horizon, escape is impossible. You would be swept inexorably towards the black hole's center, destined to be crushed by its immense gravity. The black hole's gravitational pull is so strong that it even traps light. Photons, the fundamental particles of light, are pulled into the black hole, never to be seen again. This is why black holes appear black. They absorb all light that falls upon them. At the very center of a black hole, Einstein's theory of general relativity predicts the existence of a singularity. This singularity is an infinitely dense point, a region where all the black hole's mass is compressed into an infinitely small volume. It's a place where the known laws of physics break down, a point of infinite curvature in spacetime. But quantum mechanics, the theory that governs the behavior of matter at the atomic and subatomic levels, suggests that there should be a fundamental limit to how dense matter can become. Quantum mechanics introduces the concept of quantum fluctuations and the uncertainty principle, which imply that matter cannot be compressed indefinitely. These two pillars of modern physics, Einstein's theory of general relativity and quantum mechanics, both incredibly successful in their respective domains, offer contradictory descriptions of what happens at the core of a black hole. General relativity predicts a singularity, while quantum mechanics suggests a limit to density. This fundamental conflict signals that our current understanding of the universe is incomplete. We are missing a crucial piece of the puzzle. To resolve this contradiction, we need a new, more comprehensive theory, a quantum theory of gravity that can reconcile the seemingly incompatible realms of the very large and the very small. Such a theory would bridge the gap between the cosmic scale of black holes and the quantum world of atoms and subatomic particles. The singularity at the heart of a black hole is therefore more than just a mathematical curiosity or a theoretical oddity. It represents a profound challenge to our deepest and most cherished ideas about the nature of reality, space, and time. Black holes serve as natural laboratories, cosmic arenas where the universe pushes the laws of physics to their absolute limits. By studying these enigmatic objects, we are forced to confront the fundamental limits of our current scientific knowledge and understanding. The question of what truly happens at their core could potentially reveal an entirely new layer of the cosmos, a hidden dimension of reality that we have yet to comprehend. The answer to this cosmic riddle may very well change everything we thought we knew about the fundamental nature of space and time, and our place within the vast universe. For decades, the singularity was accepted as a consequence of Einstein's equations, a placeholder for the unknown. But what if it's not real? What if it's a sign our theories are incomplete? Enter the Planck star, a radical idea from loop quantum gravity. This theory suggests space-time isn't smooth, but made of tiny quantum loops, the atoms of space and time. There's a smallest possible size, beyond which matter can't be compressed. As a star collapses, it approaches this limit, the Planck scale. At this point, quantum pressure pushes back, halting gravity's crush. Instead of an infinite point, the core becomes a finite, ultra-dense object, the Planck star. It's smaller than an atomic nucleus, yet contains the mass of a star. The Planck star is a quantum alternative to the singularity. Here, gravity is stopped by the universe's most fundamental rules. It's a new state of matter, where quantum mechanics saves the day. The Planck star is not a star in the usual sense. It doesn't burn but exists at the ultimate density allowed by nature. Imagine the sun's mass crushed into a space smaller than a proton. The energy and pressure inside are unimaginable. From the outside, nothing seems different. The black hole's event horizon hides the Planck star. Its gravity still traps light, just as Einstein predicted. But deep inside, quantum mechanics has overthrown the singularity. The Planck star replaces infinity with a finite physical object. Nature avoids a breakdown in physics, creating a new quantum state. It's a hidden core where the universe's smallest and largest scales meet. The Planck star forms through a cosmic bounce. As a star's core collapses, density skyrockets. Classical physics predicts endless collapse, but quantum gravity resists. When the core reaches Planck density, quantum pressure halts and reverses the collapse. This Planck bounce is a rapid transformation from implosion to explosion, at least from the matter's perspective. But near a black hole, time slows dramatically due to gravity. To us, the bounce appears to take billions of years. The black hole we see could be a Planck star in slow motion, waiting to explode. It's not an eternal prison, but a cosmic waiting room. The true drama unfolds on a timescale far beyond human experience. Planck stars offer intriguing solutions to some of the deepest and most perplexing cosmic puzzles that have baffled scientists for decades. These hypothetical objects challenge our fundamental understanding of black holes and the laws that govern the universe. One of the most significant problems they address is the black hole information paradox. This paradox arises from the conflict between quantum mechanics and general relativity, two pillars of modern physics. Quantum mechanics, with its precise mathematical framework, dictates that information cannot be fundamentally destroyed. Every process, no matter how complex, must preserve the initial state of a system. However, classical black holes, as described by Einstein's theory of general relativity, seem to violate this principle by erasing any information that falls into them. This contradiction has been a major headache for physicists. The Planck star hypothesis offers a potential resolution. If a singularity, the infinitely dense point at the center of a black hole, never actually forms, then information isn't truly lost. Instead, it's theorized that the information is compressed and stored within the ultra-dense matter of the Planck star, a hypothetical object that exists at the Planck scale, where quantum gravity effects become significant. Furthermore, when the black hole reaches the end of its life cycle, it doesn't simply fade away. Instead, it undergoes a dramatic transformation and explodes. This explosion releases the stored information back into the universe, ensuring that the fundamental laws of physics are upheld. The information isn't gone forever, it's recycled back into the cosmos. This process elegantly preserves the laws of quantum mechanics, resolving the information paradox and providing a more complete picture of black hole behavior. The Planck star model also fundamentally changes how we envision the ultimate fate, the very endings of black holes. It presents an alternative to the traditional view of their demise. Instead of a slow and gradual fade through the emission of Hawking radiation, a process that would take an incredibly long time, a black hole, according to this model, could meet its end in a much more spectacular and violent fashion, a powerful explosion. As the black hole progressively shrinks in size, the bounce of the Planck star at its core accelerates, gaining momentum and energy. This acceleration ultimately leads to a final cataclysmic burst of energy, marking the black hole's dramatic exit from the universe. This explosive event, if it occurs, could potentially be detected by our advanced space telescopes and observatories, providing direct evidence for the existence of Planck stars. Planck stars therefore transform these theoretical endpoints of black holes into potentially observable cosmic phenomena, bridging the gap between abstract physics and tangible reality. They offer a completely new and exciting way to rigorously test our current understanding of gravity at its most extreme limits, and to probe the fundamental principles of quantum mechanics in environments where gravitational effects are incredibly strong. Ultimately, the explosive end of a black hole, as predicted by the Planck star model, could very well be the starting point for a revolution in our understanding of physics, ushering in a new era of scientific discovery. Planck stars might connect to the universe's greatest mystery, the Big Bang. The classical Big Bang starts with a singularity, but the Planck star model suggests a big bounce. Our universe could have emerged from a rebounding Planck star formed by a previous universe's collapse. The same quantum bounce that prevents black hole singularities could have sparked the cosmos. Every black hole might echo the creation of the universe. Studying Planck stars could reveal the physics of our own origins. The end of a star's life and the birth of the universe may be two sides of the same cosmic coin. If Planck stars bounce, the explosion would be among the universe's most energetic events. The black hole would release all its stored matter and energy in a brilliant flash, not a supernova, but the death of a black hole. This could produce bursts of gamma rays or fast radio bursts, signals we already detect from deep space. Smaller primordial black holes could be exploding right now, their signals waiting to be found. Telescopes are searching for these unique bursts. Detecting one would confirm the quantum nature of space-time. The death of a black hole could illuminate the universe's deepest secrets. The Planck star remains a frontier theory, sparking new questions for science. How can we detect a Planck star bounce? What signals would prove its existence? Astronomers and theorists are working together, pushing the boundaries of observation and imagination. Could Planck stars be gateways to other universes or even create wormholes? The shift from singularity to Planck star is a revolution in our understanding of gravity and matter. The universe is more ingenious than we imagine, and its greatest secrets are still waiting to be discovered.